Okay, so next thing that we are going to consider in digital design is flip-flop timing. Now, we have seen how we can analyze and design the flip-flops in chapter 5, but we didn't talk about actually their timings because timing is really important, especially with circuits working with the clock. And we need to have the inputs needs to be ready before the clock's changing and so on. This is what we are going to see now. The setup time. Now, let's say we have got clock starting from 0, changing, going down, and so on, so forth. Train of pulse. And we have got input D, which we are going to get ready before the clock. Now, let's say this clock is working with the rising edge. Now, what is setup time is, before the rising edge of the clock, before the clock is changing, we need a short amount of time to stabilize the input, to maintain the input in the constant voltage or the constant logic level. So this short amount of time is known as T setup. Okay, so what we need to have is here, D, let's say we are assuming that D is going to be 1 before the rising edge. So it starts with 0, and when it comes over here, it will set to 1, stabilizing that setup time, and then the rising edge of the clock is happening. So the clock is changing from 0 to 1. Then we also have the hold time on the other side. Now, hold time is when it reaches to the high level, the level where the triggering is done, we need again short amount of time to maintain the input to be constant. And this is known as T hold. Okay, and that means our D input, which is 1, stays 1 until that point. And then if you want to change it to 0, you can change it after that. Okay, or if you want to keep it 1, you can keep it 1. But from this point to further, from here to there, your D input needs to be stable. Okay, so this is one of the important timing that we need to consider, that T setup plus T hold, your data input must not toggle. It's not allowed to toggle, and it has to toggle either before the setup time or after the setup time. Okay, so propagation delay, which is another metric that we consider, is in flip-flops as well. It's a little bit different compared to the combinational that we have seen at the beginning. The time interval between the triggering clock edge and the stabilization of the output to a new value. Okay, so the triggering, so clock edge, which we consider this part, and where you start to see the output stabilization, that will be the propagation delay. So if we assume that this is a D-type flip-flop, your Q is going to change. Let's say it starts with 0, initialize it, reset it. So your Q is going to change somewhere here. Okay? And it's going to be 1. Now, what we can say about this, from the triggering edge to where we start to see or stabilize the output, it's known as the flip-flop propagation delay. Okay, and then it might change again. So this is actually, the first reaction is known as the minimum propagation delay. And somewhere here, we can have TP max, which is the maximum. Then we can change to any other value. Okay, so these are some of the timing parameters that we need to know in order to analyze flip-flop timings. So here is the diagram as well. So the input is changing at this point. So when the setup time is in, it has to be stable, either 0 or 1. And then the clock is changing at this point, like we have done it. Then small amount of time is required for the hold. Again, T needs to be stabilized, and then it can change to any other value. So that's what's happening until the next rising edge of the clock. And you can see the output reaction when the clock starts changing, the triggering. The first reaction that we see at the output, which is changing to 1, output follows input, okay? And that is TP mean, and then stabilize, and it starts to change again. That will give us the maximum propagation delay, respectively. Now, these timings, T setup, T hold, mean, and max propagation delays, they can be found in the data sheet as AC timing specifications. So you can find, if you are using a discrete components, you can easily find those. And what we have already said, the daytime is not allowed to toggle. It should be held constant, where we have got setup plus hold time. During that period, it has to be constant. And the output can show up sometime between TP min and TP max. So somewhere here that we see the output, and that will be the maximum, that will be the propagation delay. So the variation between TP min and TP max can be, there will be a different vectors, high to low, low to high transition. So it's not exact amount of time that we have got at this period, okay? So multi-bit switching, operating conditions, temperatures, the supply voltage, the load, these are all affecting the propagation delay. So they can be considered, and they are not maybe specific. So the manufacturing is also affecting how this is going to be. So what we need to do with the sequential circuit time, we need to check a sequential circuit as a whole, okay? From one flip-flop or one latch to the other one. So we have to make sure that all our timing requirements are satisfied. Your D input is not coming late or arriving late to the next flip-flop. So you have enough time to reach to one point to another. These are really important if you are using a clocked circuitries. And this is what we are going to see now. We are going to see how we can analyze these sequential circuit timings and find out if we are reaching the certain point at the right time or not. Okay, if we are violating these setup and hold times, this is what we are going to see. And one of the important analysis is the setup analysis, or we say frequency max, F max. So as we are operating these in a higher clock frequency, they are result in a higher performance, so faster switchings over there, and we can obtain the outputs in a shorter time. Now, in order to calculate the maximum clock frequency, F max is given with an equation with the T min. So the minimum period is actually giving us the maximum frequency. So when we say the period, let's say, is something like this. So from one rising edge to the other, that's our period, okay? And this is period 1. Let's say period 2. As you can see, I'm switching faster. So one rising edge to another is shorter, okay? That means the frequency of this one higher than this one, okay? So this is how we can use this Fmax analysis. Now, one thing that we need to consider, the minimum clock period, Tmin, is determined by the longest delay from the triggering edge of the clock to the next triggering edge of the clock, okay? So Tmin is actually going to be the longest delay from one edge of the clock to the next triggering edge. And all paths in the circuit need to be analyzed to identify the longest path or longest delay, okay? So we always need to find the worst case. That will be our T min, and then we can find the maximum operating frequency from it. That's what we are going to see and do an example related to that. Okay, so each path delay has three components, as you can see: transmitting flip-flop, D1, and we have got some combinational logic. So transmitting flip-flop has got the propagation delay, which is equals to TP max. Combinational logic delay through the gates. We can have gates, multiplexers, decoders in there. So there's some kind of combinational circuits in there. And then we have got receiving flip-flop, and we need the setup time of that. Okay, so when we are considering the Fmax analysis, we have to consider the path of the data that is transmitting. So the input to the output, the maximum worst case propagation, plus the combinational logic propagation that we have seen. And also, this has to be the setup time, which we mentioned over here. The input coming here has to be ready. Okay, it has to be ready before it gets into that flip-flop. That's why we need to consider the setup time as well. So this is the analysis starting point, and we can draw the timing waveform related to it. And the clock starts, the propagation delay, the first one output is reached, then the first one output to the combinational logic, then the propagation delay of the combinational logic, and then from the combinational logic, whether we get the output, the time over here has to be greater than the setup time, so we don't violate. So if the input to a flip-flop doesn't stabilize in time before the rising edge of the second flip-flop, then we have a setup time violation. So we have to be careful over there. Now, setup equation is given as, based on this, let's open a new page. The setup equation so we have got the period of the clock. We can say this is T period min, okay, minus. So from this duration, we have to get rid of the propagation delay of the flip-flop 1, TPD flip-flop 1, plus the propagation delay of the combinational logic. So TPD comb, and that has to be greater than the setup time of flip-flop 2. Okay, and we know that F max is equals 1 over T period min, and we can easily find that out. Okay, so this is one of the formulas which will be used or modified in order to derive the if we are violating the setup time or not. Because if this period is less than the setup time, then we might violate it. It might arrive earlier, it may arrive lately, and this will cause a problem. So setup analysis or Fmax is given over here. Then we also have the hold time analysis. Now, while the setup analysis is done to guard against the setup time failures to the largest propagation delay, now the hold time analysis has to be done for the smallest propagation delay. So again, if I go back to here, if my input is going to change somewhere there, then that will violate the hold time. So it should not, when we have the minimum delays, when we consider the minimum worst case delays, if it's going to change or toggle before the hold time is done, then it will violate the hold time. So it will be a hold time failure. That's what we are considering. So we are considering the smallest delays, which we call it minimum propagation delays. And at this point, if the input to a flip-flop changes too quickly after the rising edge of the clock, then we will have the hold time violation. And the timing diagram for that, so the rising edge of the second part, okay, the second flip-flop is here. So the minimum propagation, okay, and the minimum combinational logic delay. So minimum propagation from flip-flop 1 minimum combinational logic delay, and then it has to be greater than the hold time of flip-flop 2. If it is less than that, it violates, there will be hold time failure. So hold equation can be given as the minimum period of flip-flop 1 plus the minimum period of combinational logic has to be greater than the hold time of flip-flop 2. Okay, so this is important as well in order to not to have any problems throughout the part. Now, another metric in these analysis is the slack. So what is slack? It's like an extra margin. So we can have a extra margin allowed in the path setup or hold time. So we can give that slack. Okay, so if we have a positive slack, that means we have got, okay, enough time to stabilize the setup and hold. If we don't have this slack, this extra margin, we are actually going to violate the setup and hold time. There will be a failure. Okay, so we'll see an examples how setup slack is, or the hold slack is violating. Now the equations are similar. So the setup slack is t period minus the flip-flop 1 plus the combinational logic plus the setup time. So when you subtract these timing properties from the period, if your setup slack is positive, that means we have got enough time. If it is negative, then we have a problem. We have to think about it for a solution. How are we going to increase the period over here so that we won't have any violation? And hold, it's similar. We have got the minimum of flip-flop 1, minimum of combinational logic, minus the hold time. This is minus because it has to be ready. It has to be ready and it should be stable after the rising edge. Okay, so that's why we have got minus over there. So let's see the first example, or how are we going to use this setup and hold slack. So assume all flip-flops in sequential circuits have got the propagation delay of 0.2 nanosecond and setup time as 0.1 nanosecond. And also assume the largest combinational delay is 1.3 nanosecond. What is the T-slack setup if the period is 1.2? So T-slack setup, we know the period, which is 1.5. So the equation is here, period minus the maximum delays and the setup time. So minus the propagation delay of the flip-flop 1 is 0.2 nanosecond plus the propagation delay of the combinational logic 1.3 nanosecond, the setup time of the second one plus 0.1 nanoseconds. So 1.5 minus 1.6. Okay, now this is actually going to give us minus 0.1 nanosecond. Now this is a problem. When we got a negative slack, it's a problem. That means we don't have enough margin with this period. So we have to do something, okay? We have to do something that we can cover this and this becomes 0. So we have enough time. So enough time because lack of this period that we don't have time. We are working at 1.5 nanosecond. But if this period was 1.6 nanosecond, then this was going to be 0. So there is a 0.1 nanosecond difference. So what we need to do is, for this negative slack, this circuit is not going to work at this frequency. And we need to slow down the clock by 0.1 nanosecond so that we can have 1.6 nanoseconds so that it works. Okay, so this is what we observe with this negative setup slack. We can have a similar things on the hold slack, and it shouldn't be negative as well. Otherwise, we are doing a hold time violation. Now, clock skew. Okay, clock skew is something, it's like a if you do remember from chapter 5, when we considered master and slave, so we have got a couple of flip-flops or the latches, okay? Q, 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 clocks. Now, these are all fitting in, okay? But the problem was, if you are using the same clock for all of those, it might be a problem that they're switching at the same time. So sometimes, in order to not do that, we can introduce, as you do remember, a inverter so that one of them is switching, other one is waiting. Now, when you include that inverter or a buffer to the clock path, we are actually getting a clock skew because of the delay of this gate over here, the inverter, your clock is going to arrive lately. Even if you have a buffer on that path, that will cause a clock skew. Okay, so we can say that 2 points in a clock network, the source of the clock skew can be gates or buffers, like we already done over here, that are placed on the clock path, or the long clock wires. It can also cause a problem. So it's undesirable, but it can be minimized to avoid timing problems. So we need to think about, if we have a clock skew and we are getting some negative slack problems, then we have to think about how we can modify the circuit in order to not to have that clock skew and meet the timing requirements. So this is an example for a clock skew where we have got a buffer in the clock path from one point to another in order to have a strong signal going into the D2, but that might cause a problem because the buffer over here might have a 0.1 nanosecond propagation delay. So when reaches over here, your clock is going to be delayed over here. It is going to arrive lately. So how do we introduce those into the formula? We have to subtract the clock skew from the equation, okay? Because this is going to add more delay over there, then we have to subtract the clock skew from the T setup slack. Now, the one thing that we can see from here, that as this is negative and this is negative, this is actually, as for the setup slack, you're actually slowing down the clock, so it might help to this slack, okay? So as you're slowing down the clock with the clock skew, it might help the slack so that you might meet the setup slack requirements. But that's not the same thing for the whole slack, because if your clock is slowed down and your hold time might not be reached, okay? So your input might change earlier than that. So that will be a problem which will hurt the slack. Okay, let's do another example and understand the setup and whole slack with the skews. So example 4, 100 megahertz clock. The buffer is 1 nanosecond. The combinational logic minimum propagation delay is 1 nanosecond and the maximum propagation delay is 2 nanosecond. The flip-flops setup time is 3 nanosecond, hold time is 3 nanosecond, the propagation delay is 2, and the propagation minimum is 2, maximum is 3, and check for any violations. Okay, so let's put those down onto a timing waveform, and you can see the flip-flop 1. So 2 nanosecond is the TP mean that you can start to observe the output, the minimum propagation, and 3 nanosecond is the maximum. And we have got a skew because of the buffer. Okay, so we have got a skew over there. As you can see, the flip-flop 2 is arriving, the clock is arriving 1 nanosecond late compared to the clock 1. Okay, there's a skew over there. So we have got the minimum and maximum propagation delays, and then we have got combinational delay and the minimum and the maximum. So after that point we reach, so we get the input for the combinational logic at this point, and then it's going to be processed. Then we have got 3 nanosecond setup time and 3 nanosecond hold time. Okay, so you can easily find these out as a 2 and 4 nanosecond and 8 and 6 nanoseconds for the propagation delays and the minimum and maximum. Okay, so let's do the calculations. Setup slack. So the period for 100 megahertz is 10 nanoseconds minus the flip-flop one propagation delay is 3 nanoseconds, and the combinational logic maximum propagation delay is 2 nanoseconds. So we are considering the maximum delays, plus the setup time of flip-flop 2 is 2 nanoseconds, minus the clock skew, which is 1 nanosecond. So 10 minus 5, 7 minus 1, it's going to be 6, right? So 6, 8 minus 1, 7. Okay, so 7 nanoseconds here and 10 nanoseconds here. Then we have got 3 nanoseconds. So we have got a positive slack over here for the setup. So positive slack means this circuit is going to work and we have plenty of time over there. 3 nanoseconds is quite a long time for sequential circuits. So let's see hold slack. So TP min for the flip-flop one is 2 nanoseconds. Then the minimum of combinational logic is 1 nanosecond. And sorry, that should be minus. The hold time of the flip-flop is 3 nanoseconds. And we also have the clock skew, which is 1 nanosecond for the buffer. Okay, so 2, 3, 3 minus 3, 0, minus 1 is minus 1 nanosecond. So we have got a negative slack. Okay, so we can have a negative slack over here. So how do we make this design work? The setup slack is positive, but hold slack is negative. Now we have got 2 ways of doing this. Now, as we have got enough setup margin over here, so we can actually push out the delay, the data from flip-flop 1 by 1 nanosecond, because if we delay this by 1 nanosecond, it will arrive 1 nanosecond later, okay, to here. So that means we can add a delay, or we can, in this case, in order to add a delay, we can add a buffer. So we can insert, each buffer is 1 nanosecond. We can insert up to 1 to 3 nanosecond, 1 to 3 buffers in order to cover that up. So the one solution is add buffers to the data path. You can add buffers after the combinational logic. The second solution, these buffers can be 1 to 3 buffers actually, 1 nanosecond each. So another alternative is, if we get rid of this clock skew here, if we alternatively route this clock, we eliminate that 1 nanosecond. So if you don't have that 1 nanosecond here, that was going to be 0. So we can say reroute clock signal to avoid skew. Okay, so we can take out the buffer and we won't have any problems. So this is how we can come up with a solution in these type of questions. Right, so we have got one more example about this. which is example 5. So we have got different paths, as you can see. So we have to do a complete analysis. The AC timing specifications are all given for us. There are no delays in the wires. Input in shows up 4 nanoseconds before and holds until 3 nanoseconds after the rising edge of the clock. The same clock is routed to all registers. There are no clock skews. Arise all at the same time, identify any hold time violations, and find the Fmax. So in order to find Fmax, we have to find T-mean, so the longest worst case delay in the path. So we have to analyze each of these paths in order to find out these violations and so on. Okay, so let's start with path 1. So what do we have in path 1? Path 1, we have got R1 flip-flop, ALU, and R4. So let's start with T period. T period 1 min, it's going to be, so the TP max of R1, which is 4 nanosecond, plus TP max of the propagation delay of the ALU, which is 10 nanoseconds, plus the setup time of R4, which is 2 nanoseconds. Sorry, 3 nanoseconds. So that's going to be 17 nanoseconds. That's the first answer. Then the T slack hold, it's going to be the minimum of R1, which is 1 nanosecond, plus the propagation delay. There's no min max, it's just average, so 10 nanoseconds again. And the hold time of R4, it's going to be 2 nanoseconds, so minus 2 nanoseconds. So this will give us 11 minus 2, 9 nanoseconds. So that's path 1. Repeat the same thing for path 2 and the other paths. So TP 2 min. So path 2 is from R2 to R3. So R2 TP max is 5, plus we don't have any combinational logic. So R3 setup time is 1 nanosecond, which is going to give us 6 nanoseconds. Then T slack hold 2 will be the TP mean of the R2, which is 3 nanoseconds, minus the hold time of R3, which is 1 nanosecond, and that is 2 nanoseconds. So far, we don't have any violation in the hold. Then we do the same thing for path 3. So TP 3 min equals, so TP path 3 is R4 to R5, and we have got a multiplexer in between. R4 TP max is 5 nanosecond, plus the multiplexer for 4 nanoseconds, plus the setup time of R5 is 1 nanosecond. So it's 10 nanoseconds. Then the T slack hold 3, that's going to be TP min of R4, which is 3 nanoseconds, plus the mean, the multiplexer, so 4 nanoseconds, minus the hold time of R5, which is 1 nanosecond. So this is going to be 7 minus 1, 6 nanoseconds that we have got. So that's path 3. Path 4. So TP for min. Now for TP for min, path 4, we have got R3 to R5. Again, multiplexer in between. So R3 max is 4 nanosecond, plus the multiplexer, another 4 nanosecond, plus the setup time of R5, which is 1 nanosecond. So that's going to be 9 nanosecond. Now, T-slack hold 4, the mean of R3, 1 nanosecond, plus 4 nanosecond propagation minus hold time of R5 is 1 nanosecond. Okay, so then this is going to be 5 minus 1, it's going to be 4 nanosecond. So we have got path 4. And path 5, TP5 min. Now, path 5 is R5 to R6. So R5 to R6, we have got R5 max, which is 4 nanosecond, plus the setup time of R6, which is 3 nanosecond. Then this is 7 nanosecond. And we repeat for T-slack hold. So that's going to be the minimum of R5, which is 1 nanosecond, minus R6 hold time, which is 2 nanosecond. Now we have got minus 1 nanosecond. So we have got violation over there. There's a timing failure. So I'll just put those reds over there. Let's carry on and then we'll talk about it in the end. So path 6. So TP6 min. So path 6, we have got R6 to R1. So R6 TP max is 5 nanosecond. Plus, we have got 4 buffers, and each of them are 2 nanoseconds. So that will give us 4 times 2, 8 nanoseconds. Plus the setup time of R1, which is 1 nanosecond. And that will be 14 nanoseconds. And T-slack hold 6 is going to be, so the TP mean of R6 is 3 nanoseconds. And the buffers is again 8 nanoseconds. And the hold time for R1 is 1 nanosecond. So this will give us 10 nanoseconds. So path 7. So TP7 min and R2 to R4. So R2 TP max is 5 nanosecond plus the ALU 4 nanosecond plus the setup time of R4, which is 3 nanoseconds. So this will give us, sorry, ALU is 10 nanosecond, that will be 18 nanoseconds. Then T-slack hold 7. So TP mean of R2, 3 nanosecond. Then 10 nanosecond for the ALU, minus the setup time of R4, which is hold time of R4, which is 2 nanoseconds. This will be 11 nanoseconds. Okay, so now we can easily see that there's one hold slack failure, okay? And the largest delay that we have got in TP min, we have got PAT7. If we look at the other ones, so let's identify. This one has got 17, 6, 10, 9, 7, 14, and 18. So that's the largest delay that we have got. So PAT7 is the speed limiting path. That means F max is going to be 1/18 nanoseconds, which will be 56 megahertz. Okay, so that's the F max that we can find based on PAT7. Now, for the failure, as it is 1 nanosecond failure, now PAT5 hold time needs to be fixed in this case. So as we have got plenty of setup slack, which is 7 nanoseconds, we have enough over there. We can actually add a buffer over here, just one buffer between two. So we can say add buffer between two flip-flops. It's actually sort because we are going to delay the data, then it won't be any problem. It will be fixed. So you can see the solutions on the slides as well. Timing failure identified. PAT7 is the last one and it's the limiting one. And that's what we are going to get. So in order to fix the failure, we just add buffer between these two, delay the data, and there won't be any problems.